Hello everyone. Thank you very much for checking this video out. I'm a professor in the Department of Mechanical Engineering at Virginia Tech. The purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we see the mass time acceleration term. And on the right-hand side, we see the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in stark contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other and how, if we have one molecule here, say, for example, a lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side, we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he try to optimize the flow near a race car so that we can reduce the drag, right? He or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So, however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. In this video, we explore the importance of chemistry in electroosmosis. So the concept of electroosmosis is like this. So anytime that you have a solid surface, when they come into contact with the electrolyte, oftentimes a charge will develop on the surface of your solid. So this surface charge could be either negative or positive, often depends on the pH of your solution. Shown here, we have a solution that actually helped to develop a negative surface charge on the wall of your channel. So in this case, because of this negative charge, positive charges in the electrolyte are pulled towards it, and while negative ions are pushed away from it. This will help to form what we call the electrical double layer or double layer salt. In this double layer, the net charge of the ions is not zero, and they have to balance the charge on the solid surface. So therefore, if you apply a tangential electrical field, what you end up with is that there is a net body force driving the fluids inside the electrical double layer. And this driving force will make the fluid near the wall move, and this fluid then move further the fluid in the center part of the channel. And this is what we call to generate electroosmosis. So now electroosmosis is very widely in handling fluids at the micro scale and nanoscale. The reason for this is electroosmosis, the velocity, the magnitude of the velocity here is independent of the size of the channel as long as the channel width is much bigger than the double layer thickness, which is typically true because double layer thickness in the aqueous electrolyte can get as big as about 0.7 micrometer only. So hence the electroosmosis has found a lot of applications in devices like lab on chip, where you have numerous microchannels and fluid has to move within these channels. So now the continuum, or the classic fluid dynamics view of electroosmosis, actually is very simple. So what we have is that now here the fluids actually are treated as a continuum characterized by two parameters, the dielectric permittivity and the viscosity. And so now the ions are just nothing but point charges, and the wall usually have a no-slip surface with charge density of sigma. So now with this information, you can use the so-called Poisson-Boltzmann equation to predict the ion distribution. Once you have that, you inject that into a Navier-Stokes equation to generate the body force to move the fluid. So what we would like to here to ask is, what if we have a very smooth wall that actually carries a net surface charge? In that case, would the classic fluid dynamics be adequate in describing the flow? So it turns out that the carbon nanotube is a very good model system to answer this question, because carbon nanotube, as we know, has an extremely smooth surface. And now if we knock out some of these surface atoms and functionalize them, then we can get a net charge. So that would be a good model system for us to test the continuum theory. So what we could do now is that we could build a molecular model for this problem. And shown on the left is a model that we built for the carbon nanotube. We have a nanotube that has a diameter about 5 nanometer in diameter, and we put discrete charges on the surface. So this way we generate a charged carbon nanotube. It could be either negative or positive depending on the charge that we put on these black dots. So next we put sodium chloride solution into the nanotube, and the end result are shown on the two figures here. So on the left figure, we have surface charge density is about 0.07 coulomb per meter square with chloride as a contact. And the right hand side, we have the opposite surface charge density, sodium ion as a contact. So now if you ask the continuum theory to predict what is going to happen, it will tell you that, well, if you use the opposite electric field, one pointing down and one pointing up, then these two flow generated in these two systems is going to be identical because surface charge is opposite and the ions are both single valence ions. So is this what we are going to see in the empty simulation? Well, we don't know yet until we run the simulation. But the good thing is that we know some of the chemistry unique to ions and water molecules and nanotube are built in our system. So this serves as a good model system to test whether chemistry actually plays a more important role than the classic fluid dynamics would have assumed. So now here's the result, right? So what we found is that shown here is the velocity across the nanotube as a function of radial distance. So when the surface is positively charged, right, so we get a gigantic flow, and when the surface is negatively charged, the flow essentially vanishes. So what this means is that when we flip the surface charge density, right, so the flow actually did not go as what the continuum theory would predict. So why is that? So well, we can answer this question by looking at the water and ion distribution across your nanotube. So shown on the figure on the right is when the surface charge density is positive and chloride are the counter ions, and we say that the water molecule has a sharp layer formed near the carbon nanotube surface, and near the wall we have a significant accumulation of chloride ion. This is fully expected because our wall is positively charged in this case. So now, important observation is that this chloride ion are a little further away from the surface compared to the water molecule, and this is very much expected because the chloride ions are bigger compared to the water molecules. So although chloride ions actually are in contact with the carbon nanotube walls, right? So they are slightly further away from the surface. And this allows the water molecule to provide some sort of lubrication for the sodium chloride ion, which will be important as we shall see later. So now the situation is different if we change to the negative surface charge density. Here, sodium ion are the chloride ion. So the water density profile is similar as what we've seen before, but the sodium ion distribution are very different. What we say is that they form a very sharp peak here. And if you look at it, right, so this sodium ion actually became contact absorbed on the carbon nanotube wall. However, because their size is smaller compared to the water molecule, right, so we see that their location is actually closer to the wall than the first water layer. So this will make it more difficult for the water molecule to lubricate the sodium ion's movement. And this turns out also to have some interesting consequences. So with this distribution, then you could still ask, right, so why, when chloride ion absorb on the surface, we still get considerable flow, well, but when the sodium ion absorb on the surface, we don't have that. Well, this turns out to have a little more chemistry in it. So to illustrate that, right, so what we do is we study the dynamics of the contact, or in fact all the ions inside the channel. So on the left figure, we show when the surface is positively charged, right, so chloride are the counter ions. So what we say, we release the chloride ions at z equals to 0 here and watch their trajectory. And shown here is their trajectory in the z direction. So what we see is that the contact absorbed chloride ion actually have a pretty good mobility. They can still move around, very much similar to what we had in the bulk part of the channel. So in another word, right, so although these chloride ions are in contact with the wall, they actually can still move with reasonably high mobility. And so the reason for this is because the major force that impedes the movement of the chloride ion actually is the electrostatic attraction between the charged surface and the chloride ion. And here the chloride ion turns out to be a little bit big. In fact, they are bigger than the water molecule. So their kind of attraction is not enough to pin the chloride ion to the surface. Therefore, chloride ion still can move around, and the force that we apply to them using electric field can be transmitted to the fluid. Therefore, the fluid can move, and we end up with high speed. So now the situation is very different when we go to a negatively charged surface. So in this case, right, so again, we plotted the trajectory of sodium ion, right? So what we say here is that this sodium ions here actually are the sodium ion contact resolved on the carbon nanotube wall. We see they have essentially no mobility. In another word, they are pinned to the surface. And the reason for this is actually entirely chemical, and that is, if you look, right, so the sodium ion actually is smaller. So therefore, the electrostatic force between the charged wall and the sodium ion is stronger, is much stronger compared to that of the chloride to the wall. So this much stronger force actually could pin the sodium ion to the surface. Therefore, when we apply an electrical field, right, so the force that we applied is actually transmitted to the carbon nanotube wall rather than to the fluid. So consequently, the fluid experiences no driving force, and this is the reason why we say that there is negligible electroosmosis when the surface is negatively charged and the sodium ion get contact resolved on the wall. So through this example, we see that the chemical details, right, so in this case, the size of the ions actually plays a fundamental role in the flow. And this kind of role is neglected in the classic hydrodynamics, and such they are not able to predict the electroosmosis as we think from the MD simulation. So if you are interested in the further analysis, more quantitative analysis of the result here, please refer to this paper published in 2003 in Nano Letters, and some of this work is also documented in a dissertation.